In this video, we are going to explain arc length. First, we have to find the length, this length, by Pythagoras theorem, which is Ln is equal to xn squared plus yn squared and everything square root. And try to imagine we make these triangles smaller and smaller, and the equation will be summation n equal to 1 to infinity and square root the formula. And the second equation, we find the gradient, which is f prime x. Find the gradient, and the gradient is yn over xn. And we substitute this equation to the previous equation, and we get summation n equal to 1 infinity square root xn squared plus f prime x and xn squared. And you simplify that equation, you will get limit k equal to infinity and summation n equal to 1 to k and square root 1 plus f prime x squared and dx here. And the final equation will be integrate b a, this one, and square root 1 plus f prime x squared dx. And this is the equation of arc length.
Okay, so this is our first example in the question that involves arc length. In this question, we are required to find the arc length of the curve of fx equals to x squared from x equals negative 1 to x equals to 2. For us to use this formula, first we have to differentiate fx. F prime x equals to 2x. And then we'll substitute this value into this formula, which is arc length equals to integrate from negative 1 to 2 square root 1 plus 2x squared. And here we can apply this technique from chapter 8.3, which is the trigonometric substitution, where this is a triangle. The hypotenuse is equal to square root 1 plus 2x squared, where this is 1 and this is 2x and this is theta. Now we will let 2x equals to tangent theta and x equals to tangent theta over 2. This is because tangent theta is equals to opposite over adjacent, which is 2x, and dx equals to secant squared theta over 2 d theta. And when we change this from dx to d theta, we have to change the limits. When x equals to negative 1, theta equals to negative 63.435, and when x equals to 2, theta equals to 75.964. And now we'll substitute everything back into this equation. Arc length equals to integrate with the new limits square root 1 plus tangent squared theta secant squared theta over 2 d theta. And as you can see, this is actually 1 over 2 secant squared theta, and since 1 over 2 is a constant, we can bring it out. And 1 plus tangent squared theta is actually equals to secant squared theta. And secant square root of secant squared theta is equals to secant theta. So now we have 1 over 2 square root, 1 over 2 integrate secant theta, secant squared theta. Previously we were left with the half integrate secant theta, secant squared theta, and from there on we'll have to use the integration by part. We'll let u equals to secant theta and dv equals to secant squared theta d theta. And du d theta equals to secant theta, tangent theta, and v equals to tangent theta. And the next step to apply the integration by part would be uv minus integrate v du, and now we'll have half tangent theta secant theta minus integrate tangent theta secant theta tangent theta d theta. And we'll just multiply this in, and we'll have tangent squared theta secant theta. And as we know, tangent squared theta is equals to secant squared theta minus 1. And now we multiply this in, we'll get secant cube theta minus secant theta, and we can separate that out into two different integrals. And now we have half tangent theta secant theta minus integrate secant cube theta d theta plus integrate secant theta d theta. And as we know, this part is also equal to integrate of secant cube theta. So we can just pull this out since it's exactly the same. We pull this out since it's a minus. We pull this out to the other side. So now this, excluding this, is equals to 2 integrate secant cube theta d theta, and we can pull the 2 from the other side back onto this side, and dividing this entire equation by 2. So now we have 1/4 tangent theta secant theta plus integrate secant theta d theta. And as we solve this, we have 1/4 tangent theta sec theta plus ln modulus secant theta plus tangent theta. And as we solve this by substituting the limits in, we have 6.13, which is the answer. Okay, so this is our second example on an arc length question. In this second question, we have to find the arc length for the curve y equals to ln sec x from x equals to 0 to pi/4. Similar to the first question, the first thing we have to find would be the dy dx. Which is secant x tangent x over secant x. And this is equal to tangent x. And now we'll apply this into the formula. Arc length equals integrate 0 to pi/4 square root 1 plus tangent square x dx. And as we know, 1 plus tangent square x equals to sec square x. So the power and the root cancels off each other, so and as we integrate this, we'll get ln modulus secant x plus tangent x from 0 to pi/4. And as you solve this, you get the answer to be ln square root 2 plus 1. And this is the answer.